Hello students. So in this video I will be taking some more examples on the properties of LTI system. Here it's a different kind of problem is given. So the problem is, consider a system with impulse response h of n is equal to 2 to the power of minus n u of n. If the input to the system is x of n is equal to 2 delta n plus 4 delta n minus 1 plus 4 delta n minus 2. Calculate, the first thing is output y of n for values of n varying from 0, 1, 2 all the way to 6. So that means we have to apply values for n from 0 to 6 in y of n, and we have to find out the value of y of n. So that is the first part. And second one is compute the stability of the system. That means we have to check whether the given system is stable or not. In the last video, we discussed about the properties of LTI system, which are memoryless, causality, stability, and invertibility. And we took some problems, examples on them, and we verified whether the system possesses these properties or not. Okay. So in this video, the first part of the problem is to find the values of output y of n, and here a new thing is an input x of n is also given. Now to verify the system, we will be using only the impulse response of the system. So to get the output y of n, so the first thing is we have to simplify the equation and bring it to a form. That means the y of n should be expressed in terms of impulse response only. Okay, so how to do that? So let's begin with this one. Let y of n is equal to h of n convolved with x of n. So I will be going with h of n convolved with x of n, and here I have substituted the values h of n, and x of n value is 2 delta n plus 4 delta n minus 1 plus 4 delta n minus 2. Now we have a property of impulse response, that is, if you convolve any signal with delta n, you will get the same signal at n is equal to 0, whatever the index that delta n is representing, that is what you are going to get here. If it is at origin, you will get x of 0. If it is at delta 1, you will get x of 1, like that. So based on that, if I take h of n convolved with delta n, then I will get h of n only. And if I convolve h of n with delta n minus k, that is a time shifted version of impulse function, then I will get h of n minus k. So this is a property. I am just refreshing that. Now we are using these two here to simplify our equation. Now you can see this h of n is convolved with entire x of n signal. Now when h of n is convolved with 2 into delta n, so we will get 2 into h of n here. Okay. Now then h of n convolved with 4 delta n minus 1. So 4 is the amplitude, I am keeping as it is. So h of n is convolved with delta n minus 1, that will give h of n minus 1. So this property, and h of n convolved with 4 delta n minus 2 will give us 4 into h of n minus 2. So this is the expression we got. So we have expressed y of n in terms of h of n, and then here I have substituted the values of h of n here. So 2 kept as it is, h of n is 2 to the power of minus n into u of n. I will just go through here and I will show you this h of n, it is given 2 to the power of minus n into u of n. In the same way, 4 kept as it is, I want h of n minus 1, so then it will become 2 to the power of minus of n minus 1 u of n minus 1 plus 4 into h of n minus 2 is there, 4 to the 4 into I think supposed to write 2 to the power of 2 to the power of minus of n minus 2 into u of n minus 2. So this is the equation 4 into. Okay. Now this is the expression for y of n we got. Now we have to find the values of y of n for n varying from 0, 1, 2 up to 6. So I will take some example, I'll apply some values for n, and I'm not going to solve all of them. I will show you some 2 to 3 values how to apply this. And in the same way you apply the remaining values and simplify to get the output values of y of n. Okay. So first, for n is equal to 0, so for n is equal to 0, that means y of 0 is equal to 2 into 2 to the power of 0 into u of 0. Okay, sorry about that. 4 into 2 to the power of minus 0 minus 1 u of 0 minus 1 plus 4 into 2 to the power of minus 0 minus 2 u of 0 minus 2. So let's simplify this. 2 to the power of 0 is 1 and u of 0. So based on the definition, u of n is present for values of n greater than or equal to 0. So that's why u of 0 is 1. So 2 into 1 here plus 4 into here minus is there. So 0 minus 1 is minus 1, minus into minus plus. So that means 4 into 2. And here you can see this is u of minus 1 here. Again 4 into 2 to the power of plus 2 u of minus 2 here. Now from the definition of impulse response, for negative values of n, our unit step function will be 0. So that gives us 2 plus 4 into 0. This term will become 0. 0 into 0 is 0 plus 4 into, again u of minus 2 is also 0. So if you simplify this, you will get y of 0 as 2. So this is for n is equal to 0. Now for n is equal to 1. For n is equal to 1, y of 1 is equal to 2 into 2 to the power of minus 1. Okay, I am applying the value 2 to the power of minus n is there. I am applying n is equal to 1 here. Next, u of 1 plus 4 into 2 to the power of minus of n minus 1 is there. So that is 1 minus 1. U of n minus 1 is there, plus 1 minus 1 plus 4 into 2 to the power of minus 1 minus 2 u of 1 minus 2. So if you simplify this, you will get 2 into, this is 1 inverse, that I will write it as 1 by 2, and u of 1 is there. So u of 1 for positive values of n, u of n is 1, so that will be 1 here, plus 4 into, so 2 to the power of 1 minus 1 is 0, so 2 power 0 is 1 into, so this becomes u of 1 minus 1, that is u of 0. So u of 0 is 1 for n is equal to 0, so that's why this is also 1, plus 4 into, now 2 to the power of 1 minus 2 is there, that means you will get 2 to the power of minus 1, that is plus 1. And here you have u of 1 minus 2, that is u of minus 1. You can avoid one more step, or if you want more clarity here, okay, let me put it like this, into u of 0 I'll put here, and into u of minus 1. So this one, 2 into u of minus 1. So this 2 to get cancelled. 1 into 1 is 1 plus 4 into 1 into 1 plus this becomes 4 into 0 because u of minus 1 is 0. So finally we'll get the value like this. So this is 0 here, 1 here, 1 plus 4 into 1 into 1 is 4 plus 0, that is equal to 5. So y of 1 is equal to 5 here. Okay. So I will try one more value and I'll leave you the remaining values for you to try. That is 3, 4, 5, 6. So let's go for y of 2. So 2 into 2 to the power of minus 2 into u of 2 plus 4 into 2 to the power of minus 2 minus 1 u of 2 minus 1 plus 4 into 2 to the power of minus of 2 minus 2 u of 2 minus 2. Okay, now 2 into 2 square is 2 to the power of minus 2. I will write 1 by 4 into u of 2 is 1 plus 4 into, so this is 2 minus 1 is 1. So 2 inverse, that is 1 by 2. So u to the power u of 2 minus 1 is there. So u of 2 minus 1 is u of 1, that is 1 here, plus 4 into 2 to the power of 0 is 1 into u of 2 minus 2 is 0, u of 0 is 1. So 2 it cancel. So that is 1 by 2 plus 2 ones, this is 2 times, so 2 into 1 is 2 plus 4 into 1 into 1 is 4. Okay, so that means 4 plus 2 6, 6 plus 1 by 2, it's 6.5. Okay, so this is y of 2. So in the same way, you have to apply the values for n is equal to 3, n is equal to 4, n is equal to 5 and n is equal to 6, and you have to find the values for y of 3, y of 4, y of 5, y of 6. So anyhow, I will give you the values for y of 3. You can verify this. So y of 3 you are supposed to get 3.25 and y of 4, so you should get 1.625 and y of 5 should get 0.8125 and for y of 6 you should get 0.4062. So hope you will go through the remaining values and verify this whether you're getting the same or not. Okay, let's go to the next stage, that is the B bit. So first part is over. To find the values of y of n for n varying from 0 to 6. Second one is compute the stability of the system. Okay. Now it is a discrete time LTI system. So for a system to be stable, the condition is summation k is equal to minus infinity to plus infinity h of k. So the impulse response, the summation of impulse response should be less than infinity, or it says that the impulse response should be absolutely summable, then only the system is stable. So let's substitute the values for h of k here. So k is varying from minus infinity to plus infinity. Now h of k I want. So h of n is equal to 2 to the power of minus n into u of n, that is given. So that becomes 2 to the power of minus k into u of k. Okay. Now the limit, apply the limit. So we have u of k here. So u of k is equal to 1 for k greater than or equal to 0, and it is equal to 0 for k less than 0. So this u of k will be 1 for the duration of k greater than or equal to 0. So that means our limit is from minus infinity to plus infinity, which changes from 0 to infinity, because only for positive values of k, u of k will be 1. So therefore, S is equal to summation k equals 0 to infinity, and we have 2 to the power of minus k. Okay. So just for my convenience, I will substitute this further. K is equal to minus 0 to infinity 1 by 2 k. So from the geometric series, we have summation n is equal to 0 to infinity a to the power of n can be written as 1 divided by 1 minus a. So where a is not equal to 1 or a is less than 1. So this is the condition from geometric series. Now we can apply the same here. So in place of n we have k, and limit are same, 0 to infinity, 0 to infinity. In place of a we have 1 by 2, and in place of n we have k here. So the limit and this term are the same, so we can apply that. So that gives us 1 divided by 1 minus 1 by 2. So if you simplify this, so that will be 1 divided by 1 by 2, that will be equal to 2. So this value is a finite value which is less than infinity. Okay, so that means our impulse response is absolutely summable. So therefore, we can conclude like this: since is less than infinity, so this condition is satisfied, the system is stable. Okay, so this is the verification of stability property, and the system is stable. Okay, so let's move on to one more problem, one more example here. So here in this problem, it is given that a LTI system with impulse response h of n is equal to 0.99 to the power of n u of n plus 3. Okay, check whether the system is stable, causal, and memoryless. Okay, now this is the problem given. So let's take one by one. So first, let's verify for stability. So it's a discrete time system. So therefore, the condition for a system to be stable is S is equal k varying from minus infinity to plus infinity h of k. This should be less than infinity value. Okay. Uh, so S is equal to summation k varying from minus infinity to plus infinity. So let's substitute the value here: 0.99 to the power of k, and u of k plus 3 is given. Now this we have to take the limit here. So I am directly writing this limit. So u of k plus 3 is equal to 1 for k plus 3 greater than or equal to 0, and it is 0 for k plus 3 less than 0. Now if you simplify this, we'll get k greater than or equal to minus 3 and k less than minus 3. So that means for values of k which are greater than or equal to minus 3, u of k plus 3 is 1, and for values of k which are less than minus 3, u of k plus 3 will be 0. So this is the limit here. So our limit changes from summation k is equal to minus 3 to infinity 0.99 to the power of k into 1. Okay. Now we have the limit varying from minus 3 to infinity. So I just want to change it from, for my convenience, I am trying to bring this to some standard geometric series form. So what I'll do, I want to make this from 0 to infinity. So make that happen, I will replace this k with some other value. I put m is equal to k plus 3. So if I put m is equal to k plus 3, or you can write as put k is equal to m plus 3. So let's see what happens to the limit. So the lower limit is m plus 3 is equal to, I think m minus 3 will be better. M minus 3, my mistake. Okay. So m minus 3 is equal to minus 3. So m is equal to minus 3 plus 3. So I will get the lower limit as 0. Now if I go for upper limit, m minus 3 is equal to infinity, m is equal to infinity plus 3. So m will be infinity only. So this allows me to make the limit from 0 to infinity. Okay. So I replace k with m minus 3. So I got my limit from 0 to infinity. So if this happens, then I have to substitute k with this m minus 3 value, or m is equal to k plus 3 in other words. So let's do this. Therefore, S is equal to summation m equals 0 to infinity, and here I had 0.99 to the power of k. So k I am replacing with what? M minus 3 here. Okay. Now let's simplify this. I will take this point, if you split, I will take this 0.99 to the power of minus 3 outside the summation, and I will leave with m is equal to 0 to infinity 0.99 to the power of m here. Okay. So this is similar to summation m is equal summation n is equal to 0 to infinity a to the power of n, that is equal to 1 divided by 1 minus a. Now I can apply this. So 0.99 to the power of minus 3 into 1 divided by 1 minus 0.99. Okay. And now if you simplify this further, you should get some 103.06. You'll get this value if you further simplify this, and that will be less than infinity here. So just to save some time, I am not going to the detailed simplification of this. So you just simplify this, you will get this answer 103.06. So that means we have getting a finite value, so which is less than infinity. Therefore the system is stable. So you can conclude it, since S is equal to 103.06 is a or is finite, comma, the system is stable. Okay. So next is causality property. the condition for causality is h of n should be 0 for n less than 0. Okay. So let's try it out. Given h of n is equal to, so what do we have as h of n? So we have 0.99 to the power of n u of n plus 3. Okay. Now if I put n is equal to minus 1, so h of minus 1 is equal to 0.99 to the power of minus 1 u of minus 1 plus 3. So that gives me, this is 1 divided by 0.99, which is almost equal to 1, and u of 2. Now u of 2 is 1 here, 1 by 0.99 into 1, so which will be approximately equal to 1 only. So that means for negative values of value of n, my impulse response is not equal to 0. So that means the condition is not satisfied. So we can conclude like this: since h of n is not equal to 0 for n less than 0, comma, the system is not causal. So it is not a causal system. And if we check for memoryless, so given the condition, the system should be of this form, the impulse response should be of this form, then only the system is said to be memoryless. So given h of n is equal to 0.99 to the power of n into u of n plus 3. So if you compare this and this, the equation is not satisfied. So therefore, so h of n is not in the form of c into delta n. Therefore, the system is not memoryless. Okay. So this is the conclusion for this. Now I'll take one more example here just to show what is the condition for a system to be stable. So here a system is given with impulse response h of t is equal to 3 into delta 3. So again check for stability, causality and memoryless. Okay. So we have to verify for these three. First I will take stability here. So it should be absolutely integrable, then only we can say that the system is stable. This is the definition of a stability property. So let's simplify this. So tau varying from minus infinity to plus infinity, h of tau is there. So that means given 3 into delta t, that is 3 into delta tau d tau. Okay. Now delta tau is present only at the origin. So this limit won't apply. So this delta tau is present only at origin because delta t is equal to 1 only for t is equal to 0 and it is 0 for t not equal to 0. So delta t is present only at the origin and the value of delta t is 1. So that allows us to say that 3 into 1, that is equal to 3. So the limit is not from minus infinity to plus infinity. So it is present only at origin means, so we will consider only that point, and in the origin the value of delta tau is 1. So 3 into 1 will give the value 3 here. So 3 is a finite value which is less than infinity. So therefore the system is stable. Okay. So now if you go for causality, the condition for the system to be causal is h of t is equal to 0 for t less than 0. So given system h of t is equal to 3 into delta t. So put a negative value for this. So h of minus 1 is equal to 3 delta minus 1 here. Now as I mentioned here, delta t is present only at the origin, and any apart from that its value is 0. So delta minus 1 is 0 here. So therefore 3 into 0 will give you 0 only. So that means for negative values of t, the impulse response is 0. So therefore this condition is satisfied. Since h of t is 0 for t less than 0, the system is causal. Next, memoryless. So condition of the system to be memoryless means it should be of this form. The impulse response should be of this form, that is c into delta t. Then only the system is said to be memoryless. Given h of t is equal to 3 into delta t. So now you can observe this, c is a constant. So here in place of c we have 3 here, and delta t is there, and this is also delta t. That means the impulse response is satisfying the condition of memoryless. So that means the system is a memoryless system. So conclude like this: since h of t is of this form, that is it is satisfying the condition, the system is memoryless. Okay. So I have taken some examples in this video. This may be a little bit lengthier, but I hope you have understood the method how to verify the system for the properties of LTI systems. Okay, and I will give you some examples for you to try and apply this methods and verify the following properties. And all this problem you verify for check for causality, stability, and memoryless. So verify all these systems for these three properties and see what answer you are going to get. Okay. Anyhow, in the next video, I'll be moving towards step response. But before that, I want you to try some problems on your own. So that's why I'm giving this to you. So first one, a system with impulse response 1 by 2 n into u of n. So for this system with impulse response h of n is equal to 1 by 2 n u of n, check for all these properties. And the second one, h of n is equal to minus 0.5 to the power of n into u of n. Okay. Third one, take h of t is equal to e power minus t u of t plus 100. try one more here, which is similar to the previous one, but try it out. E to the power of 2t u of t minus 1. So try these four examples and verify for the properties of causality, stability, and memoryless. Hope you have understood this method, and if you have any queries, do reply or comment on this video. Thank you for your time.